So here we are in section 7.2. So we're going to get into exponential notation for nth roots. We're going to define and use expressions of the form a to the m over n. That's what it means by rational exponents. It's a fractional exponent. And we're going to convert between radicals and rational exponents. And then we'll use the rules for exponents, which we've already done before, but we're going to deal with them using rational exponents or fractional exponents. So the first thing, we're going to use exponential notation for nth roots. So here's the idea. We've seen this nth root of a already. We've seen that. We can rewrite this as a to the 1 over n, a to the 1/nth, which is the same thing as taking the nth root of a. If you'll notice, what happens here is the denominator of the fractional exponent is the index. So if we had 4 to the half, that's the same thing as the square root of 4. Our index, when we're dealing with the square root, is 2. So the denominator of the fractional exponent becomes the index when we write it as a radical. So here we have 8 to the third. Notice that the 3 becomes the index of the radical expression. So we're actually taking the cube root of 8. And here we have 16 to the fourth. We'll notice again the denominator of the fractional exponent becomes the index of the radical. And that's what it says here. Notice the denominator of the rational exponent is the index of the radical. So we're going to evaluate each one of these. So first we have 32 to the fifth. That can be written as the fifth root of 32. Notice that the denominator of the fractional exponent becomes the index of the radical expression. So 64 to the half is the same thing as square root of 64. The index here is 2, which is the denominator of the radical exponent, the rational exponent, sorry. And then here we have negative 81 to the fourth. Remember, we do the exponent first, so this negative part isn't going to come into play here. The negative is after we take the exponent. So what we're dealing with here is the fourth root, because remember the denominator becomes the index of the radical. So we're taking the fourth root of 81, which is 3, and then we apply the negative. Now D, what we have here actually in D is we're trying to take an even root of a negative radicand. And remember, we can't do that. We say that that's not a real number, right? Because the radicand is negative and the index is even. So looking at E, you might think, well, we can't do that. But actually what we're doing here is taking an odd root of a negative radicand, which we can do. So what we do is we take the cube root of negative 64, which is negative 4. Now, F, what we're going to do here, we're going to take the cube root of both the numerator and the denominator, because remember, the denominator of the rational exponent becomes the index of the radical expression. So what we did was take the cube root of 1, which is 1, and then we took the cube root of 27, which is 3. Remember, we can break those up into the numerator and the denominator. So here we are, objective 2, define and use expressions of the form a to the m over n. All right, so if we have m and n as positive integers, and it's the fraction mnth is in lowest terms, then we can say that a to the m over n is the same thing as parentheses a 1/nth parentheses to the power of m. Now this makes sense because of the power rule, right? Because if you remember, using the power rule, we would multiply the exponents, right? Remember, we multiplied the exponents. And using the rules of multiplying fractions, this is the same thing as m over 1. Remember, m times 1 is m, 1 times n is n, so we end up back over here, a to the m over n. This is going to be very important when we simplify these things. And by the way, if, for example, a to the 1/nth is not a real number, then a to the m/nth is not a real number either. And remember, the way that a to the 1 over n would not be a real number is if we were taking the even root of a negative number a. So here we go. 25 to the 3/2. We can rewrite that as 25 to the half to the third because of the rule we just explained there, and kind of the reverse of the power rule. And remember, 25 to the half is the square root of 25. So we take the square root of 25, which is 5. And now we apply the other exponent, which is the third, and we get 125. Now in B, 27 to the 2/3 can be written as 27 to the third squared. We're just undoing the power rule, right? And and then 27 to the thirds is the same thing as the cube root of 27. And the cube root of 27 is 3. So now we apply the square exponent here, and we end up with 9. Now something interesting is going to happen with 16. First off, you might say, I've got an even root here of a negative number. Remember, we do the exponent first. So first we take 16 to the half, and we take that to the 16 to the half to the third. We keep that negative on the outside. Remember, 16 to the half is the same thing as the square root of 16. So we take the square root of 16, and remember, we do the exponent first, so we cube 4, and then we apply the negative. Now D, if we rewrite that as negative 64 to the third, which is the same thing as the cube root of negative 64. Remember, we can do this because we've got an odd index in a negative radicand, right? So we can do that. So we end up with negative 4. Then we square negative 4, and we get 16. Now, E is not a real number. Ask yourself, why is this not a real number? It's not a real number because what we're doing is taking the square root of a negative radicand. We're taking the square root of a negative number. Remember, we say that they're not a real number if we take the even root of a negative radicand. That's why that is not a real number. So this goes back to what we talked about in the previous chapter on negative exponents. So a to the negative m/nth, which is what we're talking about here, is the same thing as 1 over a to the m/nth. So what we've done is just when we have a negative exponent, we've moved it to the opposite side of the fraction bar and then applied the exponent. So this is the same rules that we've kind of talked about before. The only difference is we're dealing with a fractional exponent in these cases so far in this chapter. Now, here's another way to think about this, we've talked about this where we sort of take out the m. We're kind of doing reverse power rule. Another way to think of this is this a to the m over m can also be a to the mth to the power of 1 over n. Multiplication, remember, is commutative, means we can change the order in which we multiply, and we end up with the same number. So if that is true, then this other form here is also true. As long as we keep the n in the as the index, we can apply this m exponent to either the outside or into the radicand itself. And this is based upon this previous rule that we talked about when we have rational or fractional exponents. So this next objective here is we're going to convert between radicals and rational exponents. So here we are. So it wants us to write each exponential as a radical. All right. So 19 to the half. So remember, the denominator is the index. So this is actually, and then the square root of 19, because the index is assumed to be 2 whenever we're talking about a square root, right? Now we're going to write 11 to the 3/4 as a radical. So what we do is we put the denominator into the index portion of the radical expression, right? And then there we've represented it as a radical. Now C, we just factor out the 14. The x is to the 2/3. We take the x, the index, the denominator of 3 becomes the index of the radical expression of x, and then we move the square to the outside. In D, once again, the denominator becomes the index, and then we move the third to the outside of the parentheses. And here again, the denominator of the rational exponent becomes the index of the radical, and then we move the numerator to the outside of the parentheses. And remember, x to the negative 5/7, we can write that as we move the base along with the negative exponent to the opposite side of the fraction bar. So this becomes 1 over x to the 5/7. And F, we apply that special rule. 3 is going to be the index, and we move the radicand, whatever the base of the fractional exponent, we move that into the radicand portion there. So again, there we have the index is 3, and the radicand is x cubed plus y cubed. So now we're going to write each radical as an exponential. So right now our index here is 2, so the square root of 37 can be represented as 37 to the half. We just moved our index to the denominator of the fractional exponent. Now h, something special is going to happen here. This is the same thing as 8 over the 9 to the 8 over the index, which is 4, and 8 divided by 4 is 2, so it becomes 9 squared, or we can write that as 81. Now let's just look at I here. It becomes Z. Ask yourself why it becomes Z. Actually, it becomes Z because we're going to have Z to the 8 over 8, and 8 over 8 is 1, so what we end up with is Z to the first. So here we are, objective 4, use the rules for exponents with rational exponents. So we're just using the same rules that we've talked about regarding exponents here, just the case is they just happen to be fractions. The exponents happen to be fractions in this case. What we mean rational exponents here. Here we have the product rule. Remember, when we multiply like bases, we add the exponents. Then we have the rule for a negative exponent. Remember, when we have a negative exponent, we move the base with the appropriate exponent to the opposite side of the fraction bar. Then we have the quotient rule. Remember, when we have like bases in a quotient, we subtract the exponents. And then here's a special rule for negative exponents. Remember, we just move the bases to the opposite side of the fraction bar. And we also have a little bit of the quotient, the power rule over a quotient going on here, which is right here. Power rule over a quotient. We apply the exponent to both the numerator and the denominator. Then we have power to a power. Remember, when power to a power, we multiply. And when we have a product to a power, remember, we apply the exponent to both of the factors in the product. And then here's just another one of the special rules for negative exponents. We can turn it into the reciprocal of the base raised to the exponent. Now the exponent becomes positive. So here we are. So we have like bases here. So we're going to simplify each one of these expressions. Well, as always, we write using only positive exponents. So what we have here is 3 to the half times 3 to the third. We have them like bases. We're going to apply the product rule. So we're going to do 3 to the half plus a third. Now when we add fractions, remember, we got to find a common denominator. So a half becomes 3/6, and 1/3 becomes 2/6 when we're finding the common denominator. We go ahead and add those up, and we got 3 to the 5/6. Then now B, we have a quotient. So what we're going to do is subtract the exponents, right? Because we have a like base of 7. So we subtract the exponents. Luckily, we already have a common denominator there. End up with 7 to the negative 2/3. Remember, we want to write these using positive exponents. So we get 1 over 7 to the 2/3. We just applied the rule for negative exponents there. Now in B, several things are happening. The first thing we're going to do here is we got b to the 2/3 over b to the first. So of like bases, we're going to subtract the exponents, which is what they've written here as 2/3 minus 1/3 as a base of b. Now 2/3 minus 1 is the same thing as 2/3 minus 3/3. That's how we end up with negative 1/3. Now we apply the 6 to this product here, and we do that by multiplying the 6 times the appropriate exponent there. So we've got, using the rules of multiplying fractions, we got 6/3, and we a to the 6/3, and we got b to the negative 6/3. So what that becomes is a to the a squared, and then we got b to the negative 2, which we've got to write using positive exponents. So we end up with a squared over b squared. So in this next one here, what we're going to do is distribute the r to the 2/5 here. So basically, when we were applying the product rule, right? Remember, when we apply the product rule, we add the exponents, which is what they're doing here, by adding r to the 2/5 plus 3/5, r to the 2/5 plus 8/5. We add those using the rules for adding fractions there. And we got r to the 5/5 over r to the 10/5. R to the 5/5 reduces down to r to the first, and r to the 10/5 reduces down to r squared. 10 divided by 5 equals 2. Now these just are to just help us to learn a little bit more about these rules. We're applying the rules for rational exponents. So the first thing we do is write the radical as an exponential. Now we've got x to the 3/4, which we put the index of 4 into the denominator. Here we put the index of 5 into the denominator. So that becomes 3/4. X to the 3/4 times x to the 5th. We've got to add those. So we find a common denominator of 20. Now we add our numerators. Remember, that's how we add fractions. So we got x to the 19/20th. Now first we got to write b as an exponential. So we put the index of 2 into the denominator here. We applied the 5 to the numerator. Here we put the index of 3 into the denominator. So remember, now we have a quotient here of the like bases. So what we're going to have to do is subtract the exponents. We find a common denominator of 6, and 5/2 becomes 15/6. 1/3 becomes 2/6. So we subtract those exponents there, and we end up with x to the 13/6. Now C, we're going to first rewrite it as an exponential. The first thing is x to the 6th, cube root of x to the 6th. We rewrite that again as an exponential. So now what we do is we're going to apply the power rule by multiplying these exponents here. 1 times 1 is 1. 3 times 6 is 18. So we got x to the 1/18.